Welcome to Schools Not Out, your daily classroom for CSEC and CAPE students. You can watch this lesson real-time on Television Jamaica's YouTube channel or One Spot Media. We're also live on Music 99 and GoJamaica.com. If you have any questions on today's subject, you can send them into Television Jamaica's Facebook page at Television Jamaica or Instagram at Television_Jamaica. Today's lesson is on Seasick Physics. We're focusing on forces and motion. I am Pethorn Dawkins. Welcome back, students. This morning we're going to deviate a bit from the topics that we're looking at in the fifth form level. I realized that the fourth formers, they were missing out somewhat with regards to all the topics we've looked at thus far. So by the time school had closed, you pretty much would have started looking at forces and motion, Newton's laws. So this morning, that's what we're going to do. Forces and motion, and of course, the topic called momentum. Now, a little background information. What is a force? A force can be expressed as any influence that causes a change in the state of motion, direction, and/or shape of the object. And as the pictures here depict, we have a shutter blasting off, that's a change of motion. We have a ball bouncing, that's a change of direction. We also have a ball, then that's a baseball, being hit by a baseball bat. And these basically display what forces can do. Rocket blasting off needs a force. A ball changing direction needs a force. A ball being deformed by a bat also needs a force. So any influence that causes 1, 2, or 3 of these things will be considered a force. Now, as with any physical quantity, they are measured by a specific unit or a standard unit. Forces can be quoted in various units. So for example, when you go to the market and they tell you that, well, they're selling X item for X amount for X pound, pound can be considered an informal unit for force, but there's an SI unit. SI meaning Standard International for the unit of force, and that's the Newton. And if you have never heard the name before, Isaac Newton, yeah, it was named in his honor. So it is the equivalent to the base units of the kilogram meters per second squared. When we start looking at the units, rather the laws of motion, you'll see why these base units come out. But just know, the standard unit of force is the Newton. Here I have a table displaying other units that may be used to quote force, the dyne, the gram force, the pound force, kilogram force. You may see these units coming out, especially if you go higher up in physics, but just know that each has an equivalent to the Newton, and it is shown on the far right of your screen. But just know for now, at this level, especially at the fourth form level, you just need to be aware of what the force and the unit of force is. Now, we can classify forces in one of two ways: contact or non-contact. Contact forces, they require a physical connection to be transmitted, all right? Non-contact, they don't require such a physical connection. You can transmit them through physical connection, but if you separate the objects, they still can be applied. As a matter of fact, they can be applied in a vacuum where there's nothingness. All right? So examples of contact forces: applied force, spring force, drag force, frictional force, normal force. All these forces require something touching another thing for them to be applied. If there's no touching, then you cannot apply a force to a spring without touching it. Doesn't make sense. If you're able to do that, then quite frankly, you have become something greater than I. All right? Now, for non-contact forces, these are the magnetic force, the electric force, and the gravitational force. All right? So when you're dealing with magnets, north and south pole, when you're dealing with electric force, positive, negative, when you're dealing with gravitational force, masses being attracted, these things can be attracted across a distance. They don't need physical connection to be applied. Forces types. Now, forces can be transmitted through one of three actions. Either you push, which really is causing the object to move away from where the force is applied. You pull on it, it moves towards where the force is applied, and you twist it. So when you push a door, you apply the force, you're the source of force. The door starts moving away from you. If you pull the door, it moves towards you. Twisting a door, I don't think they really have materialized twisting doors to open them, but if you are able to twist something, what it does is that it spins or rotates about a fixed point. All right? So as the diagram shows here, she pushes the pram, she's pulling that object, and then she's twisting a rag. Twist, push, and pull are ways forces are applied. The effects, as mentioned before, force can cause a change in the state of motion. For example, if you kick a stationary ball, it moves from not moving to moving, right? And the states of motion are shown there. Either you're not moving or you're moving at a constant speed. You're not just moving. You have to state how you're moving, and that's at a constant speed. For the direction, you can either be vertical, horizontal, diagonal. The ball is there, was heading down diagonally. It bounced, it heads up diagonally. Force caused that. And of course, a shape. The ball that was spherical, when you squeeze it, it becomes non-spherical. A force is required for that. So these are the effects of forces. Now, balanced and unbalanced forces. From Form 3 or Grade 9, you should have learned about balanced and unbalanced forces. So we're just going to go through it real quickly. Forces operate in a pair, and Newton's third law will tell us that. What do I mean by a pair? P-A-I-R, they operate as two, never one but two. And they're either balanced or unbalanced. If they're balanced, they're said to be equal in value. If they're unbalanced, they're said to be unequal in value. Now, if you have balanced forces acting, then what will happen is that because they oppose each other, forces oppose each other, especially when you're dealing with Newton's third law, they cancel each other to give what they call a zero overall or net force. So pretty much it's like the tug-and-war game as shown down below. If you have, say, 10, 20, a million persons on one side, team A, and you have however many persons you want on the other side, if they are applying together the same force, but in opposite direction, nobody wins, because one force cancels the other. That's balanced. However, if the forces are unbalanced, then the smaller force will subtract from the larger. And that will now result in an overall net force. And the value of it is, of course, the difference of the two forces, and the direction is the direction of the greater force. So pretty much, if you look at the diagram below, 300 newtons, 300 newtons, they balance, cancel. Fine. Nothing happens there. You're just pulling, wasting energy, but nothing takes place. Now, if the team on the left starts pulling stronger, say 400 newtons, and team on the right now can't pull any harder, 300 newtons, then we have no unbalanced. The unbalanced force or net force is the difference of the two, which is, of course, 100 newtons. And the direction is, of course, to the left where the 400 newtons point. And that will now cause, of course, the team on the left to win. Simple? Right. So that's how balanced and unbalanced forces work. Now, we're on to Newton's laws of motion. Now, you probably would have heard about action and reaction already. You probably would have heard about a force causing something to speed up, slow down, but you probably didn't hear it put now in a standard or an official way. So my friend Isaac Newton here, he did some work sometime in the 18th century, and he formulated some laws that basically describe how objects move under forces. And you can predict based off how his experimentation was done. So he looked at now how forces affect the motion of objects and predicted the behavior of objects while moving under the influence of forces. And there are three laws: the law of inertia, first law; force and acceleration, the second law; action and reaction, the third law. I'm going to look at each in a bit detail. First one, the law of inertia. Now, if you have never heard of the term inertia, and it's not inertia, it's inertia, that's fine, it's a physics term, but just know that you experience it every day. And the best way to think about it is if you're in a vehicle sitting or in a bus standing, and the driver of the vehicle makes sudden maneuvers. Starts speeding up rapidly, starts slowing down rapidly, takes a sharp corner, your body now will respond to that. If you're moving and you draw a sudden break, you feel yourself thrown forward. If you're sitting down or standing up, and the unfortunate situation, you're not holding on and the driver suddenly moves off, more than likely you'll be falling on your back. All right? The reason for that is because your body naturally wants to stay in that state of motion as it is. And remember, the states of motion that we looked at before is either you're moving at a constant speed or you're not. So if you're sitting in a bus or standing in a bus and you're not moving, the bus starts to move, you don't naturally start to move immediately. You resist that. And that resistance to moving or starting to move or changing your state of motion is what we call inertia. So, first law can be called the law of inertia. The statement official is, and you should already know this, objects that are at rest or stationary will remain at rest, and objects that are in motion will continue along a straight line at the constant speed and direction unless acted upon by a net force. So pretty much as I said, if you're standing in a bus, the bus is not moving, you're not moving, nothing needs to happen to you for you to maintain that. If the bus starts to move, then you start to fight that. A force is applied on you and you start to fight that. If you're moving in the bus and the bus, as them normally say, draw a sudden brake, you will feel yourself thrown forward. It's not that a force throws you forward. Really what happens is that the bus stops, but you don't stop because of your inertia again. So what happens is that you continue to move even though the bus stops. And that is really what the first law is talking about. So inertia, natural tendency of all masses, every piece of mass, to maintain their current state of motion. It happens naturally, you don't have to do anything. They want to stay that way. All right? Inertia will resist any change in the state of motion, and you need a force to do that. If there's no force, then you continue as you are. If there is a force, your body fights it, but you will eventually respond to that force. The diagram here shows object at rest remains at rest. You kick it, it starts moving. Ball that's moving will continue to move until, of course, the net stops it. First law, inertia, object will not change its state of motion unless acted upon by an unbalanced, or the same thing, net force. The larger the mass, the more force you need. So heavier objects or larger masses require larger forces to move them in the same way. All right, so if you move something and it feels light and you put some more mass in it, you now have to apply a greater force to get it to move because you now have added inertia, you have added the resistance to start moving. Second law, force and acceleration. So this is now where the force comes in and what happens when there is a force. For a given constant mass, very important, the acceleration, and acceleration is how quickly you speed up or slow down. If you're moving at a constant speed, you're not accelerating. All right, your speed is not changing. But if you do speed up, your speed increases. If you slow down, then your speed decreases. So acceleration is really what that is, speeding up, slowing down. So the acceleration experienced by that mass is directly proportional to the net force acting. Now from math, you should have learned proportionality. Proportionality essentially means if 2 results in 4, then if you double 2, then 4 must double. If you make 2 half as much, then 4 becomes half as much. That is how proportionality works. 1 causes something, then if you change that, then the other now will change in a corresponding way. Doubling 1 doubles the other, making half results in half. All right? So pretty much, force causes acceleration. So whatever force causes an acceleration, if you want to change the acceleration, you change the force. If you double the force, the acceleration will of course double. So here we have a diagram. Force being applied to the trolley causes an acceleration, the speed increases. If you apply more force to the same trolley, naturally you would have gotten more acceleration. Another case, the same force, but now we're looking at a ball versus a car. Now what do you think will happen? Well, based on the fact that there is a different mass but the same force, remember, more mass, more inertia, more resistance. So what happens is that a larger mass for the same force does not want to speed up as much as you do expect it to. So that's what happens. Force on the ball, large acceleration. Same force on a car, small acceleration. Make sense? Hope it does. Now, second law carries an equation. And this is the equation. Remember the magic triangle I keep telling you about? 2 things to combine to give a third? Right. So this is how the magic triangle stays for Newton's second law. At the top, you have force being F. Below, mass and acceleration M and A. So to get force, multiply mass by acceleration. To get mass, cover mass, force over acceleration. And of course, to get acceleration, force divided by mass. All right? So this pretty much sums up the second law and how you manipulate the equation. All three equations are given there. How you manipulate them to get the different equations. All right? Newton's second law, the unbalanced force acting on an object is equal to the mass of the object times its acceleration. All right? So the unit of force is the Newton of, as we said before, N. And remember, the equation, the units that we spoke of earlier on, kilogram meters per second squared, is shown here. So 1 Newton is equivalent to 1 kilogram meter per second squared. So we have a situation where the mass that was combined with the acceleration equivalent to the Newton. All right? So pretty much when it comes on to the units, that is how you get the actual units of acceleration. Kilogram meters per second squared, but they now use the Newton in honor of Sir Isaac Newton. But pretty much it's the same thing that was discussed before. Same force, small mass, large acceleration. Same force, large mass, small acceleration. Now, a quick question. What force is needed to accelerate a 10 kilogram shopping cart at 10 meters per second squared? So we have a 10 kilogram shopping cart, and we're given the acceleration of 3, is it? Meters per second squared. All right, and we're asked for the force. Now, if we go back to the equation I was given in a triangle, we see that force is just simply mass times acceleration. So we put the 10 kilograms with the 3 meters per second squared. Oh, this and that is the same thing. I just like to write it like that. And that gives us 30 kilogram meters per second squared. Or if you want, you can just write simply newtons. All right? So that's a simple math. Just multiply the two values. And for the other two questions, you simply multiply the values because they're all asking for force. Force for the second one, force for the third. 5 times 1.2, that will give you 6 newtons. 50 times 2 gives you 100 newtons. You can just work that out in your free time. Right. Moving on now to third law. Action and reaction. Now you probably would have heard that whatever you do in life, it will come back around to you, karma, that type of thing. Yeah. But in physics, really and truly, what we're talking about now are forces. And as I said before, forces act as a pair, P-A-I-R. If body A, and this body A can be anybody, from as small as an atom to as large as a planet. If body A exerts a force on body B, so we're talking about two separate objects here, all right? Body A, B. So if A exerts a force on B, then B, that was the second object, will now simultaneously exert an equal and opposite force on A. All right? So if I push on something, whatever that is, it will push back on me with the same value of force, but in the opposite direction that I push. So if I push towards the screen and something is there, that thing now will push back at me behind me. The initial force from body A is termed as the action. So that's where the term action comes from. So it's the action force. And the response force from body B is termed as the reaction force. All right? So as the diagram shows here, and if you have ever had this unfortunate opportunity or situation where you're stepping from a boat and the boat gives way and you fall in the water, it is not because the universe is out to get you. It's just simply physics in action. What happens is that for you to get onto the platform there, you have to apply a force to push you forward. The water doesn't provide a lot of friction. It doesn't lock the boat in place. So the boat now is free to move whenever it wants. So you push on the boat. By action or reaction, the boat will try to push on you. But guess what happens? The boat is pushing on the water and the water is not pushing back. So the boat will move because of your force, and you will try to move because of the force that is there, but it's not enough. So the boat moving, you don't move, guess what happens? You can't float and you can't hover, so you'll fall in the water. Don't worry, you'll just get wet, hopefully. All right, so we have here some different diagrams showing third law, a gun being fired, recoil is as a result of the bullets going forward. That's what causes the recoil in a gun. Person there stepping from the boat moves, the person tries to move forward. We have here in the bottom left of the screen a rocket blasting off. The gases, they're forced downward, and the rocket moves upward. So that's what happens for the rocket to move upward. You have to force exhaust gases down, and that gas being forced down, action or reaction pushes the rocket up. Same thing for a balloon. If you've ever blown a balloon up and you release it, don't tie it, but just release it, you realize that it moves off in all different directions. Yeah, it's not really magic of sorts. It's the air that you trapped in it that is now being forced out. So that trapped air is forced out because of the force on the air. The air, of course, because of third law, pushes back on the balloon. So the air moves back, balloon moves forward. Diagram on the right shows the same thing. Bullet fired, recoil and gun. When you move, when you step, that is why sometimes if the ground is slippery, your feet moves backward when you try to push forward. It's because you now push forward on the ground, and the ground now having or should be having traction. They call that the special force of friction between your foot and the ground. So if there's traction, you move forward. If there's little traction, then your foot just simply slips. All right? So action and reaction is what moves you forward, and of course the same boat situation. So without friction, without traction, nobody will really get anywhere fast. All right? Now, moving on to force and circular motion. Now, circular motion is a special kind of motion where objects move in a circular path. It's not like your typical moving vertically upwards or downwards or away or towards. What we have now is an object literally tracing out a circular path going round and round. It doesn't get away or towards anything, it just goes around in a circle. Now, what does force have to do with circular motion? This type of motion is one in which the mass continuously follows a circular path around a fixed point under the influence of a net force. So just imagine you having a ball with a string, you're spinning it around, you know, like the hammer throw when they have with field events in Olympics or sports day, right? That's an example of circular motion. This type of motion is constantly accelerated. Why? The velocity of the mass changes continuously even if its speed remains the same value when the mass moves in a circle. Now the reason for this is because acceleration is said to be a vector. You should already know about vectors. Vectors have magnitude and direction. So here's the thing. An object can move at a constant speed in a circle, yeah? But because moving in a circle means that it's constantly changing direction, then it is actually accelerating, because acceleration is a vector and a vector has direction. So if the direction is changing, that means that that quantity is also changing. All right? And once it is changing, then if it's velocity, or if it's speed with direction is velocity, and once it's velocity that's changing, then you have an acceleration. All right? It's just the reasoning of it all. All right? So once you have that acceleration, Newton's second law tells us that you need a force. So that is how the force comes in. For circular motion, this net force points towards the center of the circle and is called the centripetal force. Fancy Latin name, comes from a Latin origin. All right? Centripetal forces can be contact or non-contact. Contact meaning a ball and a string. Non-contact, quite literally, moon being held in its orbit around the earth. Gravity pulls moon towards earth, earth towards the moon orbits the earth, and as a matter of fact, the earth orbits the sun due to gravity, and they move in a circular path. And the origin must always be present to maintain the circular motion. If the force is removed, then the moving object will continue in a straight line instead of a circular path from the exact point the force is stopped acting. So it's like this. Object is moving in a circular path, direction is constantly changing. Now, it maintains a circular path due to the force that acts inward. If that force is removed, naturally, because of first law, it will continue to move in a straight line path. Now, imagine that happening to our solar system. Imagine, like, I don't know, God just decided that, all right, I'm going to just test something, because God is in control of that, right? And he just, just say it just switches off gravity. You'd imagine that everything that's moving now does start moving off in straight lines. Everything, well, Earth, for example, because that's where we live. We would literally be in trouble. Because where we are right now is just enough that we don't freeze to death or burn up. So quite literally, if the gravity were to be switched off, then we'd be in problems because we just fly off into outer space. All right? So we have to bear that in mind. When we're moving in a circular path, something needs to keep it there. Ball that's moving, you need a string. No string moves off in a straight line. The velocity here is always changing. It's here, then it's here, then it's here. Direction is always changing. When you take a corner with a car, circular motion as well. That is why cars either maintain the corner or they slide off the corner. It's either you have the force to do it or you don't. All right? That's how circular motion works. All right? Now, onto linear momentum. Momentum is that physical quantity that combines the mass of an object with its velocity. It is a vector. It has magnitude or size as well as direction. Its direction is the same as the velocity of the mass. Its value is found by multiplying the mass value of the object by the velocity the object has. The units have a combination of mass velocity units through multiplication. All right? But we're going to leave momentum here for a minute, and just going to take a break and come back. So if you have any questions on what we have done for you so far, you can send them in on our various platforms, and I will see if I can answer them in the final segment. When we come back, we'll answer your questions and wrap up. Stay with us.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing with a tissue and dispose of it. Avoid close contact with anyone with a cold or flu-like symptoms. If you become ill, please visit your doctor or the nearest health center and share your travel history. The flu and coronavirus can kill. Let's protect each other. A message from the Ministry of Health and Wellness.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.
COVID-19 tip. Protect yourself and others from getting sick by washing your hands after coughing or sneezing, when caring for the sick, before, during, and after you prepare food, before eating, after toilet use, when hands are visibly dirty, and after handling animals or animal waste.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing with a tissue and dispose of it. Avoid close contact with anyone with a cold or flu-like symptoms. If you become ill, please visit your doctor or the nearest health center and share your travel history. The flu and coronavirus can kill. Let's protect each other. A message from the Ministry of Health and Wellness.
Welcome back to School's Not Out, your daily classroom for CSEC and CAPE subjects. Today we have been discussing Seasick Physics, forces and motion. Alright, so before the break, we were looking at circular motion and we'll kind of just jump prematurely into linear momentum. So I'm just going to just slow down, backtrack a bit to just ensure that we get this whole thing about momentum. Now, it is a physical quantity, like anything else in physics that we have been looking at. which combines the mass of an object and its velocity. All right, two things combined. It is a vector. Remember I was talking about this vector thing? The other thing is scalar, but we're not looking at that. It is a vector, it has magnitude, which is the size, as well as direction. So you have to consider both. Its direction is the same as the velocity of the mass. So whatever direction the velocity vector has, the momentum vector will have the same direction. Now, its value is found by multiplying the value of mass of the object by the velocity value of the object. Its units are a combination of the mass units and the velocity units, and they multiply. All right, so whatever units you use for mass, be it kilogram, gram, pound, whatever, you use those units, whatever the units for velocity, meters per second, kilometers per hour, mile per hour, you just combine those two and you get the units for momentum. It is possible for different mass values to have the same momentum, since velocity also affects the momentum value. So don't just think that, all right, hey, once you have a large mass, then naturally you will have more momentum than a smaller mass. No. You combine the two, and then you look at now the value you have for momentum. To increase momentum, you either increase the mass or the velocity, or you can do both. And the opposite is true. So if you want to decrease momentum, you make the mass smaller, the velocity smaller, or you make both smaller. Either way, it will affect your momentum value. As with most things in physics, there is an equation, and it is this for momentum. They term it as sometimes linear momentum because there are other forms of momentum. There's angular momentum and all of that. But for now, you just need to know that momentum and linear momentum are the same thing. Now, the symbol is P. I don't know why. I've always asked myself this over the years. They have chosen P. Let's just work with it. So the symbol for P, the symbol for momentum is P. And of course, mass is m, v is velocity. The arrows over p and v are just simply indicating that they are vectors, and they point the same way. SI unit, remember that standard international, is kilogram meters per second, because the SI unit for mass is kilogram and SI unit for speed or velocity is meters per second. So SI unit for momentum, kilogram meters per second. Momentum is a vector, as we said already. Its direction coincides with the direction of velocity, as we said already. Now, a quick question and a trivia actually. Rank the following objects from the smallest to the largest in terms of their momentum values. Now we have a 100-gram bullet moving at 250 meters per second. That's extremely fast. A 4-kilogram bowling ball moving at 5 meters per second. That's basically a little jogging speed. A 60-kilogram sprinter running at 10 meters per second. That's pretty much top speed for most sprinters. A 1,200-kilogram car rolling at 0.4 meters per second, and a stationary 10,000-kilogram train engine. Now, which of these do you believe would have the greatest momentum? Which would have the least? Your guess is as good as mine without the calculation. But we do have the calculation. I'm going to give you a few seconds to just calculate that real quickly as I move over to these slides. Now, the 100-kilogram bullet, converting that to kilogram, is 0.1. When you multiply that out, that gives you 25 kilogram meters per second. The 4-kilogram ball at 5 meters per second, that's 20. 60-kilogram sprinter at 6 meters per second, that's 360. The 1,200-kilogram car rolling at 20 centimeters per second, when you convert that to meters per second, it's actually 0.2, and that gives us 240. And a stationary kilogram, 10,000-kilogram train engine is actually 0. Yeah, because since you multiply mass and velocity, 0 times any value gives you back 0. So it is illuminating to see that actually the heaviest or the most massive object has the least momentum, simply because of its velocity being 0. And it's also interesting to see that, well, the sprinter actually has the largest momentum. You'd think that the bullet now would probably be up there high. No. Because of its small mass, then its momentum comes down to be very small. So when we rank them from smallest to largest, we have the train engine, the bowling ball, the bullet, the car, and lastly, the sprinter. Yeah, that's how momentum works. All right? Now, we're going to look at collisions as it relates to momentum. A collision can be considered as a physical interaction between two or more masses in which there is an exchange of momentum and or energy. You would have already been privy to momentum, but energy, the energy we're talking about here is kinetic energy. By now you should have been exposed to that. If you're not, just know that kinetic energy is mass and velocity squared over 2. There are two types of collision, elastic and inelastic. For your elastic collision, this is where your total, and it's very important, the total kinetic energy and the total momentum of the masses remains unchanged or they are conserved. These kinds of collisions are ideal and they rarely ever happen in nature. The reason for this is because anytime something collides, some energy is always, or can always say almost always lost. When something bounces, you hear it. That's energy, sound energy. If something hits somewhere and you see a spark, that's light energy. So once you have any form of energy loss, then it is not conserved in terms of its energy. And once you do not have energy being conserved, then it is not elastic. All right? But if you have total energy and total momentum being conserved, then you have an elastic collision. So therefore, the real collisions are inelastic. These are ones now only the momentum, total momentum of the masses remain unchanged. The energy undergoes some change and most times it is a decrease. Inelastic collisions are real and everyday and between masses and they are a bit more complicated to analyze than elastic. So the ideal situation is better to look at. The unideal or the unideal is more complicated, but it's the real thing that happens. All right? Now, here's a diagram showing a completely elastic collision before, and this is for persons who play pool. You've seen this before, I hope. The cue ball hits the 8 ball. Immediately after collision, the cue ball stops. The 8 ball now moves off with the velocity that the cue ball has. So this is roughly an elastic collision. All of the kinetic energy of the cue ball is transferred to the 8 ball. So it moves off with the velocity that it has. If you ignore friction and the sound that it makes, then it's basically elastic. For an inelastic collision now, the ball here hits this one. But you see, after the collision, it deforms. And deformation absorbs or dissipates or releases energy. So once the object loses energy and is converted to other forms, then the total energy is not conserved. The energy before is different from the energy after. As a matter of fact, the system has lost energy. And that makes it inelastic. All right? So we have here elastic versus inelastic. Two masses, whatever their values, they're moving at 1 meters per second. And then when they collide, they bounce off and they pretty much have the same velocity they had before. So the kinetic energy before and after, momentum before and after are the same. For this one, they have momenta before, but after they don't move. They collide, they become crumpled, something similar to like when cars collide and they come to rest and they're all mangled and damaged. Yeah, that's an inelastic collision because they had kinetic energy before. After the collision, no kinetic energy. The momenta is conserved, fine. It's always conserved. But if the energy is not conserved, then that's an inelastic. If it is conserved, then it is elastic. Now, what happens during the collision in terms of momentum? When two masses collide, both of their masses will possess a value of momentum before and after the collision. All right? The sum total of the momentum of both objects before the collision is found by adding the individual momentum values of each mass before they collide. So if you have this marker and you have this eraser and this marker, they're moving. This has a mass and velocity, this has a mass and velocity. The total momentum is the mass and velocity of this multiplied and the mass and velocity of this multiplied, and those two momenta are added. That's how you find the total momentum before the collision. When they collide, you do the same thing, mass and velocity, and you add them. That's how you find total momentum before and after the collision. It has been observed and verified that the total momentum of the masses before the collision is equal to the total momentum of the same masses after the collision. This is where we get the conservation of linear momentum principle. Alright, so before I said collisions are elastic and inelastic, but both the momenta are conserved. Well, momenta is really the sum of one, the sum of the two before and after they collide. For this conservation principle to remain, there must not be any net forces acting. So if they collide, nothing must cause them to speed up or slow down. Alright? Once you don't have any net forces acting, then the momentum can be conserved. The equation, I think it's a bit blurry, but you can see here mass and initial velocity 1, mass and initial velocity of the second object equals mass and final velocity of 1 added to the mass and final velocity of the other object. So there are two terms, two objects, four terms. Initial velocity, final velocity of both mass 1 and 2. And when you add them like that, then the momentum will be conserved. And this equation talks about momentum and energy. This is the energy equation. Half mass, velocity squared, momentum, mass and velocity of A and B, so on and so forth. All right, a quick question. I don't know if there's time for it, but we're going to try it. An 8 kilogram ball traveling east at 10 meters per second collides with a 2 kilogram ball traveling west at 5 meters per second. After they collide, they move together. Determine the final velocity of the ball. Based on the time that we have here, I can't work this question out, sadly. But I know that there are ways in which we can communicate, so we'll have to communicate on that. So that's all for today for Seasick Physics, Forces and Motion. We hope that you have grasped some of the points we have discussed. You can catch a repeat of today's lesson on JNN Today at 4 p.m. in the Schools Not Out highlights on Saturday between 1 and 4 p.m. It will also be on video on demand on One Spot Media. We'll be on a midterm break starting tomorrow, May 20th, and we'll return on Wednesday, May 27th. But you can watch the past lessons on our YouTube channel. Remember, CSEC starts June 27th, so keep studying. Until next time, I am Pethorn Dawkins. CSEC Visual Arts is up next. Stay with us.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing.